This week's lesson deals with the ideal gas law, which is a very powerful equation that relates several variables as shown here. The equation reads P times V is equal to N times R times T. We often give it the nickname PIVNERT, just as a helpful way of remembering the variables that go into the equation. I'm now going to give a quick overview of each of these variables so that you have a better idea of what the numbers you're working with actually mean. Looking at the PhET simulation from lesson number 7, we can see a pressure gauge right here that's giving us a value for the pressure inside this simulated box of gas. This value is measured in a unit called atmospheres, abbreviated ATM. When we're working with the ideal gas law, we want to use pressures that have the unit of ATM. And just as a point of reference, 1 ATM is equivalent to the air pressure at sea level, which is pretty close to where most of you live. The next variable is V, and V stands for volume, which is measured in liters. I'm now going to show you some household items so you can get a better idea of what 1 liter looks like. So here's a bottle of olive oil, and if you look very closely at the bottom of the label here, it says the volume is 1 liter. So this bottle here should give you a pretty good idea of what 1 liter looks like. I've also got a bottle of club soda here. Again, this guy's volume is just 1 liter. And finally, here is a gallon of milk. A gallon is a unit of measurement that we're pretty familiar with, but it's not one that most people around the world use. If you look down here at the bottom though, it tells us 1 gallon is equivalent to 3.78 liters. Make sure that when you're doing an ideal gas problem, you're using a volume that's measured in liters. The next variable, N, is the number of molecules in the problem. This number is measured in moles. So this actually brings back a concept that we looked at in lesson number 6. In lesson number 6, we learned that 1 mole is equal to the weight of that element or compound on the periodic table. In the case of sodium, 1 mole of sodium is equal to 23 grams. 1 mole of chlorine is equal to 35 grams. And 1 mole of sodium chloride is 58 grams, which is just a sum of both parts, 1 sodium and 1 chlorine. If the question you're working with gives you a value in grams, you will first need to use a conversion factor just like this to convert from grams into moles, because when you're using the ideal gas equation, you have to use moles. Moles are how we are counting how many molecules of gas there are. The next value is for R. R is the ideal gas constant. For our purposes, this is equal to 0.082. This constant is unique to the ideal gas law, and it's something you've got to include in every ideal gas law problem you do. Finally, the last variable here is T. This is for temperature, which is measured in Kelvin. If we return to the PhET simulation from last lesson, you can see that the temperature provided is measured in Kelvin. For any ideal gas law problem, you have to use a temperature in Kelvin. As a point of reference, 300 Kelvin is about room temperature, and boiling water is 373 Kelvin.
Example 1 states, calculate the volume in liters that 0.35 moles of hydrogen gas occupies at 1.2 atm pressure and a temperature of 310 Kelvin. Let's say that this gas is contained in a balloon. We've got hydrogen gas molecules moving around, bumping up against the walls of the balloon, creating pressure. The question is saying, how big would that balloon be if it was at 310 Kelvin and a pressure of 1.2? To solve this problem, you'll need to use the ideal gas law, PV equals nRT. First, you need to determine which variable goes with which number, and then we can use the equation and some algebra to solve for volume. Let's start with pressure. The question says that the pressure of the gas is 1.2 atm, so we'll put that in on this line. 1.2 atm. Volume is the variable we are solving for, so question mark. N represents moles, and the question states you have 0.35 moles. R value is a constant, 0.082, and temperature 310 Kelvin. Now that we've determined which number goes with which variable, we can use our equation PV equals nRT to do some algebra to calculate volume. First, we'll start with pressure, 1.2 atm times V, which is our unknown, is equal to N, which is our moles, 0.35 moles, times our R value, 0.082, and lastly times temperature, 310 Kelvin. Then we'll multiply everything on the right side. So continuing our algebra, 1.2 times V is equal to, and this is where you'll do some math, 0.35 times 0.082 times 310 is equal to 8.9. And then lastly, we'll divide 1.2 onto the other side, so V is equal to 8.9 divided by 1.2. And this will get us a volume of 7.4 liters. Make sure that you label your final answer. It's extremely important that you label your final answer. Example number 2 states your lab partner wants to add 3 grams of magnesium to a 0.25 liter flask containing excess HCl and seal the top. You know this reaction can get hot around 323 Kelvin. If standard lab glassware can withstand pressures of 3 atm, will this reaction be safe to run? The question is asking you to calculate the pressure of hydrogen gas created from 3 grams of magnesium. First, I want to fill in our variables of the ideal gas law, and then we can see what other numbers we need to calculate before we can calculate the pressure. So the pressure is what we're looking for, because we're looking to see whether or not the pressure of the gas is higher or lower than 3 atm. The volume of the flask is 0.25 liters. The moles of gas we don't have outright. It's not told in the problem, but we do have this information here, 3 grams of magnesium. We can use that to calculate the moles of H2, which I'll show in a moment. R is 0.082, that never changes, and temperature is 323 Kelvin. Now that we've matched our variable with the numbers given to us in the problem, we can calculate how many moles of hydrogen gas are produced from 3 grams of magnesium. We will use our chemical equation to help us calculate how many moles of H2 gas we can make from 3 grams of magnesium. This is a 1-to-1 ratio based on the coefficients. Therefore, 1 mole of magnesium will produce 1 mole of hydrogen gas. That means we first need to calculate moles of magnesium. 3 grams magnesium times 1 mole of magnesium. And if you look at the periodic table, you'll find that the atomic weight of magnesium is 24 grams. Because this is dimensional analysis, we can add on the next conversion factor, which is moles of magnesium to moles of hydrogen gas. It's a 1-to-1 ratio. It's a 1-to-1 ratio. So 1 mole of magnesium will produce 1 mole of hydrogen gas. And you can see that our units cancel out. And when we do the calculation, 3 grams times 1 mole divided by 24 grams, we get 0.125 moles of hydrogen gas. This number can now be used in our PV equals nRT equation. So let's insert our variables like we did in number 1. Pressure is what we are looking for. times our volume, 0.25 liters, is equal to 0.125 moles times 0.082 and times our temperature, 323 Kelvin. 323 Kelvin is quite hot. It's about 50 degrees Celsius, which is about 122 degrees Fahrenheit. So you can imagine how warm that would be. It'd be very hot to the touch. So now we multiply everything on the right side together. The left side stays the same for now. If we multiply the right side together, which is 0.125 times 0.82 times 323, you'll end up with 3.310. And now we divide 3.310 by 0.25 to isolate P, and we will get 13.2 ATMs. Again, labeling. And the question is asking if standard glassware can withstand 3 ATM, will this reaction be safe? Well, 13.2 is much larger than 3 ATM. Therefore, this is an unsafe reaction, meaning your flask will explode, which is quite unsafe.